So I'm just going to begin by saying what's wrong with programming. And, starting where they call us software engineers, but if we compare ourselves to chemical engineers, they're governed by the laws of physics. If you compare us to electrical engineers, they're governed by the laws of physics, mechanical engineers, and now we're software engineers. So what are we governed by? The laws of Windows, the laws of Mac OS, the laws of Java. We have no foundation. So what are we really engineering? Like, what does engineering even mean in the world of programming? It doesn't really have a definition. And I've been on a quest. I've been designing libraries and frameworks for more years than I can even imagine. But they always go wrong. As every piece of technology, as the years go by, it turns into trash and we reinvent it over and over again. And we're not really building a foundation. Like in physics and chemistry, we build over 1,000 years of understanding. But for some reason in the computer industry, we trash all that we knew before and we start over with some new products, some new libraries, some new frameworks, some new ideas that are all invented all over again. We really have no legacy and we're not really learning from the past. And the reason for that is we're not engineering software. We're not software engineers. If we were, then what we learned before could be applied to the future. And I noticed that as I design libraries, and this is pretty typical in the entire computer industry, version 1 is usually the best thought out. Version 2 gets a little worse, version 3 gets a little worse, and then by version 4 you're starting over, there's a next great idea, and everything that you did is trash. Well, that doesn't happen in math, it doesn't happen in physics, it doesn't happen in chemistry. And the reason that occurs after spending a long time thinking about it is that in version 1 you come to me and you say you want to build a castle. And I think about it and I come up with an elegant solution of Lego blocks. And I get these 10 interchangeable pieces and you can build the castle, you can build the walls, and with just these 10 pieces, version 1's incredible. There's no exceptions, it's very consistent. I created the perfect Lego. In version 2, somebody says, oh, you have a really cool library there, I want to build a boat. Now I have a perfect Lego set with a rope, a rudder, and a sail. It's a little bit of an exception, not too bad, but there's now exceptions to the rule and the consistency tends to break up. Version 3, somebody wants to build a car, and I have a perfect Lego set with a rope, a rudder, and a sail, a windshield, a tire, and by version 4, it's like you don't know how to use this because there's more exceptions than rule. So what's wrong? It's the Lego set is arbitrary. It's not based on any laws of physics. If you look around the universe, there's a predefined set of components. We have protons, neutrons, electrons, gravity, energy. They all come together and build this universe. So if we say that we can simulate everything in the universe and build a virtual universe, then we too should be governed by the same laws of physics. We need to start thinking of programming in a completely different way. That it is truly engineering and we're governed by the same rules that electrical engineers are governed by. What's the problem in programming? An electrical engineer can say, oh, I can design this remote control and make it half price. I'll just make the electron positive. Well, no, you deal with it. It is what it is, and it's going to be what it's going to be. But programmers cheat. It's like, I'll switch to a different language. I'll use Python. I'll use this, and I can. So we have to go back to the basics and say, okay, how do we use these particles as the Lego sets for programming? And what are they? What is a neutron in programming? Where is gravity in programming? Where is photons in programming? how do you actually build a program out of these components? And so my original quest in this was actually to find a better way of programming. I wasn't thinking in terms of using this library to actually simulate the laws of physics themselves. It's actually, I was thinking of using the laws of physics forward to build a virtual universe that you can program anything in. But as it turns out, and speaking with that a lot, you can actually go the other direction. If you build the library very consistent to the laws of physics, then you should also be able to run simulations and see what happens with this library, because now they kind of become one and the same. There's the physical world with the laws of physics, and you have a virtual world, and they're kind of interchangeable. The virtual world is just an executing universe. So when I originally started on this project, I started making all of the components, and what has kept me going as a programming model, I've scrapped this every couple of years. I scrap it and start over and scrap it and start over. The first problem that I had is, I'd create atoms, protons, neutrons, and electrons, and it's like, great. And I try to make it pretty authentic with their properties and behaviors, but then I didn't know what to do with it. It's kind of like building an F-16 fighter plane in your garage. It could be completely authentic and completely work, but you don't know how to fly it. So I didn't know how to use my original library. I didn't know where does an atom exist in programming. But over the years, scrapping it and starting over and rebuilding on it, I found an interesting thing that kept me going over the last 20 years, kind of in this quest, is that the more authentic the library became to the laws of physics, the more powerful a programming library it became. I can write things easily and much simpler in a consistent way, and I found that I can use this library to do everything. I can do 2D graphic programming, I can write databases, I can write servers. It's not like I'm using, what's popular, React for front ends and Spring Boot for back ends, and it's one library I build on top. And I also found that as my understanding of physics grew, I would take more of me out of the programming. There was a lot of things I didn't understand and didn't know how to use, so I would invent something to connect the parts. And in the next version, that piece of my own programming would come out. It would be replaced by some new law, a new understanding of physics, or the way it should be applied in programming. And so little by little, the library had more and more of me squeezed out of it, and more physics put into it, and it became a more powerful library, more powerful. So here, I want to go explain a little bit of the concepts of how far I've come, what's missing, and how I think that we need to tie it now to the math that Thad has come up with so far. And so, if you start with an atom and you have the neutrons and protons, for example, I'll forget the electrons and any other particles for right now. What I was doing in the library is making them concrete. I can have a neutron. I can put the properties into the neutron. I can give a function for how a neutron decays, and I can have a neutron decay into a proton and emit an electron and a neutrino, and these things come out, but I didn't know why they come out and why. It's just
you just made them come out.
I just made them come out. And forgetting exactly how we use this in programming, I want the next level of this library. If we can go down to a level lower, where my base for an atom would be a particle, particle, and neutrons also extend particles, and protons do, and neutrons contain quarks, and so on. So there's a very object-oriented hierarchy model of this. But the problem with all of them is I cannot convert a proton to neutron, because in classical programming, a class is a hardened formed structure that is what it is. It's not dynamic. But if we now take the neutron and the quarks and tie them and say that the base classes for the programming library is now the math itself. For example, we have a torus and the sphere. The sphere contains these toruses and hyperbolic figure 8 knots. And if we make each of these components more dynamic objects that represent the properties and behaviors of the mathematics running underneath it, then we can dynamically convert a neutron into a proton. Because there's a certain amount of turbulence, there's a certain amount of things that are executing, right? So now we can run this program kind of like in AI where you have a self-running neuron and the neurons kind of all interact with each other under their own governance, learning their own properties. We can do the same thing with subatomic particles. We can actually have chemical reactions inside of this running software. So the goal of the library is to tie the math to the running program. And now the running program should do two things. My original intent is to create a virtual universe that we can use as for true software engineering. You know, we're now on peer with electrical engineers and everybody else. We're now building software by engineering it, governed by the laws of physics. But we can also use it the other way. If this is now completely dynamic, built up from math and the geometry of the universe, we can also go the other way. We can run this as a simulation and come up with unexpected things. We can run the software, kind of like running AI, observe the chemical reactions that are occurring, and then deduce new math and figure out new things. So as we learn more about math, we end up with a better library and we can become better software engineers. And on the other hand, we can also run the program and figure out new observations. With an ultimate goal, if you think about what we're doing in CERN, we're taking particles and we smash them together at nearly the speed of light. So what we're really saying is that if we want to know how this watch works, we're going to hit it with a hammer as hard as we can and see what gears fly out. And, you know, we notice something's got completely smashed beyond recognition, but a few good springs and gears came out, so we know that. So then we take another watch and smash it again, and this time maybe the gears get pulverized, but the crystal on the watch is intact, and we know that there's a lens or something. That's a really poor way of we have to spend billions of dollars to make this equipment. And we're also limited to head-on collisions, each at nearly the speed of light. We can't do 45-degree angles or 28-degree angles, and we can't have something at nearly the speed of light and something at a quarter the speed of light. But by building this, we can actually run the program and have a virtual atom smasher. We're trying to fuse hydrogen into helium and get, energy by really pressure and temperature. But maybe there's another way. If we understand the geometry, maybe we can slide, you collide two hydrogen atoms at 25-degree angle at certain speeds, and their geometry with the turbulence will just click together, and now we have helium or other elements. If we can understand this and simulate it, now we don't need billions of dollars to do one type of test. We can actually virtually simulate all this. So there's two major gains by doing this. One is we have an executing version of the math, so we can make virtual particle colliders to see what comes out and have a better understanding. But at the same time, we change programming into true software engineering so that as we learn new things and we build new things, we find out that every 5 years or so, we don't discard the work that we did before. Like Thad coined the term, we'll actually have version 1.infinity, because once we get it right, this is our programming model that it won't change. If it's really tied with a true understanding to the laws of physics, we're now forever building libraries, just like building this house. Like the laws of physics are implied. You know, there's all these different materials, but we can study it and break it all the way down. And if we learn how to use plastics, plastics are, you know, kind of eternal. Like the way the chemical structure of plastics work will always work that way for all eternity, and we can always use it until we choose not to. It's not so in computer programming. So I think that making the leap to true software engineering would be a major leap in the way we do programming today. So we can not only build everything like building this house, but we can also go all the way down. Now, some of the things that I've found is there's a loose connection, which I'm going to go to the dimensions. And one of the things that I didn't do in the original version of this library that I'm trying to tie to the 5 dimensions of time. You know, where are the dimensions? If we try to say that you can construct software almost in a physical way, where are the dimensions? And if you look at time, that ties to the CPU clock. There is kind of a Planck time. It's the cycle speed of a computer. The next dimension, space, seems to tie to memory. Memory can be divided into 2 dimensions, 3 dimensions, however you want to view it, whatever kind of structure you want to give it. The next step up is charge, which I found interesting because if you think at a low level, if an atom represents a value, like let's say in programming you have an address record, name, address, city, state, zip. Each of these components are atoms themselves. Name, address, city, state, zip. So what is an address record? Well, that's a kind of molecule or compound. And, you know, I'll get to that later, but you can combine them and bind them together into records using chemistry. And if you think of rows of address records, it's kind of like a chemical polymer where you have repeating molecules that turn into polymers. And it turns out, I'm not going to go there right now, but it turns out you can use that to query data in very interesting ways and combine them in very interesting ways with universal ways of accessing your data, sorting it, organizing it, using chemistry on your data. And it works out, chemistry works out great for querying data and structuring data. So charge with the electrons really relates to the way data binds together into molecules and chemicals and compounds using the atom. So we do have a relationship. You do program on a charge level for creating chemistry. The next step up is mass. And where does mass appear? The mass is really the structure of the atoms and everything where the values are. And this is something that I think that, Thad, you finally figured that out, is where is values stored in a program? Like, where do numbers come from? Right? It's not like I can take an atom and, like, atoms are not like pool balls where I can say this atom is a 10, this atom is an 11. Atoms are atoms. They're not 10s, they're not 11s, they're not somebody's name. So I struggled for a long time to figure out where do these values come from in programming and how are they represented in physics. But now if you look at it from every number exists in terms of, as you're going down the time space when we're looking at these toruses that contain toruses that contain toruses, if you look at the path through it, going all the way down to the lowest number, a value represents a path. So the numbers actually are hidden in there. It's just the path. You can actually count up to the largest imaginable numbers. So now we have values, and the values are stored in the mass. And the last level, temperature, is where I use photons to represent temperature. And here is where data is communicated. It's compressed into the smallest, and at some point, like, I'll have to do a demo for you, but for doing messaging, I'm able to transmit data in a fraction of the size that we're using for like JSON and all these other messages. It compresses the data and sends it from machine to machine or from environment to environment. And one thing that we know about light is time stops at the speed of light. So you would think that in the computer world, the messages wouldn't be governed by time. And lo and behold, once you send a message from one machine to another, this clock no longer exists. It's traveling effectively at the speed of light under no time governed by no clock, unless you want to count the routers in between, until it arrives and converts back into some kind of mass where the value appears, and it's now governed by time again. Right? So these things still need work and, like a lot of thought, but I think I'm now figuring out how these 5 dimensions now apply to the programming. And I've gotten to the point where with the atoms and values, gravity also exists in program. Now, where is gravity in a program, right? It's like, after thinking about it, it becomes kind of obvious. But if we think about, we have the sun at the middle, and then we have planets orbiting. And then there's, maybe moons and different satellites around it. That looks familiar. Where have I seen that before? And then it's like, oh yeah. If you get rid of the sun and you make it a server, and the different planets are user sessions, they're orbiting the server, you can kind of think, right? You have another user session that's completely independent.
It's network architecture.
Network architecture, right? And then even within programs, one thing that I found is that there's scope, right? There's scope of variables. Even within this, you can have multiple threads running, time, but the modules themselves can have a scope. And you can get your scope going all the way up, with pointers going all the way up to the top. Anything that's global that would be in the server shared by everything is now passed down to different levels of scoping. So if you look at it in terms of gravity and center of gravity, it's exactly what you said. You have a network architecture. So the forces of gravity do exist in programming. And if we think about it that way, it's universal. If we had thought about gravity when we were designing programs in the 80s, what we would have learned and come up with would still be applicable today. Now, even neutrinos, that was one, like, it's just my gibberish, but neutrino. What is a neutrino in programming? That's a hard one because it has no charge, kind of travels at the speed of light. It's something really fast, has no mass, so you wouldn't think it contains any values.
It has mass.
Well, actually, you're right. It does have, but a very tiny, tiny, minuscule mass. But how would I use a neutrino? And like when I talked about decaying, I had a neutron that I decayed into a proton, electron, and neutrino. I kind of knew what to do with a proton. I can come back to some really interesting things you can do with protons and neutrons in actual programming values. But I had this neutrino left over, kind of like in physics, right? I have this stupid neutrino left over. What do we do with it? But then I learned one thing: not all information is lost in a neutrino. There is some information in it. Since neutrinos travel straight line and don't really interact with matter, very, very rarely they do, it does have some information in it in terms it acts as a pointer. You do know where it came from. It has a trajectory. And it's like, oh, interesting, neutrinos are pointers. So we can use neutrinos, and it has tiny, tiny mass. And what is the only thing that's in that mass that it's storing is the pointer to where it came from. So now we can use neutrinos as pointers. So if you go back, we have our network architecture in terms of gravity. Like, we're thinking in terms of physics. We have neutrinos as pointers. We have protons and neutrons. Where are they used in data and manipulation? And how can they help solve regular programming problems that we have? How are they helpful? How does it help to think of data in terms of protons and neutrons? And I'll ignore the quarks for right now. But if you think of an atom, let's say it's hydrogen and has one proton and an electron. We kind of already know where this electron is going to be used. If we have an address record with name, address, city, state, zip, we can use the electron to bind these things into a compound called address. It's like a molecule. We know where the proton is being used. It's actually going to store the value in there. The value, it'll have the name, the address. But what about the neutrons? We know that there's different isotopes of different atoms, and we know that they get heavier. So what would I put in a neutron? Well, a very common problem in programming is, let's say I have a form that has somebody's name, address, city, state, zip. And the form comes up and they're filling out some fields, and they get to the bottom of the form and they want to reset it. They change their mind. It's like they press the reset button, but now we got to get all the previous values back. Well, that's kind of a pain in programming. That means before I displayed the form, I have to copy all the values, put it someplace in memory, put it aside. They click the reset button. Oops, now I got to take these values and I have to write all this code to copy it back. Copy it back, done. Is there a better way to do this using physics? Well, if I think of this in terms of, this is a molecule or some compound, and each of these atoms, if each time they enter a new value, I make the atom heavier. I make it a new isotope. I put the previous value in the neutron. It's neutral. It's not interacting with anything. There's no electron. It doesn't hurt. It just makes it heavier, as you would expect. I'm carrying more data. So now it's in the neutron. You get halfway down and they do reset. If you reset a compound, you now decay the neutron back into the proton and electron to do the rebind, and the values all come back.
So it's going in reverse.
It's going in reverse. So you can basically have programs run in reverse and get your data back. And you can have as many in programming. It doesn't quite map yet. I think someday it may. I can make very, very heavy hydrogen, like with 50 neutrons if I want. It wouldn't exist in the real world, and maybe it wouldn't be very practical to do that. It would be extremely heavy in terms of data, which is what we would expect, but it's mirroring the physics world. We're seeing, atoms are getting heavier. And we get very powerful constructs out, ways of programming that I find when I'm programming using my physics library. Simple problems like this, I didn't design it for that. I didn't think about it for that. It was just, over time, I would be like, oh, I may want to save this. I'll put it in a neutron. We'll see what happens later. And then later on, I run into a problem. I want to reset a form. And I'm like, oh my God, I can just use physics to bring all my values back and, let this decay, get a lighter element out of it. And my programming was greatly simplified. So over the years of programming using the laws of physics, I found that very complex things started becoming simple. And another example where this is useful, I can go on, it could be an hour, many hours of different things that shake out using physics for programming, is I found I can also use electronics. If I have some kind of atom or particle, here's an atom, and I have another one, I can say atom dot diode. Now this will look similar to like Angular had, I don't know if this new version still has two-way data binding. The old one had two-way data binding. Now they're going with one-way data binding. What it means is if this value changes, if this is a diode, it's a one-way relationship. This one changes. But if this changes, this doesn't. And where they use that a lot is on the user interface. If you change the address on some form and you want it to change someplace else, you can do a data binding. Or you want a structure of data and you have the actual HTML fields, you have a value.
Now is that similar to like the functionality of like a cookie or something like that? And like that's more like a web browser side of things? Or?
Yeah, it's not quite like a cookie saves values kind of off to the side and restore that. This is more immediate, that if something changes, you can bind the value so that if this changes, that changes in sync.
This is within the coding itself rather than basically you had a reservoir of additional data.
Right. This is what they built into Angular. And different tools have implemented data binding in different ways. But if we use physics, every library ever created will have data binding built in. Once we create the diode or a conductor, if I make this a conductor relationship to this atom, that means if this changes, then this changes, and if this changes, that changes. It's like having a copper wire. Whichever way the current flows, it's going to go both directions. If it's going this way or that way, copper is copper. I also have capacitor relationships. And what that does is if this atom changes and this one, in relation to this one, this atom gets notified that there's a difference. Kind of like with capacitors, we have the two ends. There's like a difference in charge between them, but it doesn't flow. Like kind of the goal of a capacitor is to it's almost like a mini reservoir to keep your distance, right? It's kind of like a break in the loop, but there is an effect. And so where is that used? Like how is that useful when I'm drawing graphics and let's say I have a box inside of a box. If I increase the size of this and I want to increase the size in the middle, well, normally you would write all kinds of code to keep them in sync, and if this gets twice as big, you have to call routines, make this twice as big. But if you have this point over here, and you make a capacitor relationship to this point, and you don't let the value flow in. If this is 200, and let's say this is 100 in width, and this thing changes, you can have it be notified of a capacitance change. So when this doubles to 400, you take whatever this value is and multiply it by 2. This becomes 200. So now you can wire all your points together in a diagram using electronics. And now when you're dragging things with all that code that you have to write to keep everything in sync, all of a sudden starts happening magically. It's like, wow, I can use electronics to solve this problem. So I found over time, the more I use this library, the more powerful it becomes. The more authentic it comes to the laws of physics, the more I can build electronics and build nervous systems. Like I've built interacting neurons, not as neural network, but more as nervous systems for handling all event processing. One of the big problems that we have, and this kind of goes up a level almost to biology out of it, but one of the big problems where there's really no good solution is event handling and programming.
Just some thoughts. Yeah, so from a compute kind of a perspective, right? So you have a Turing machine. So what I wanted to sort of draw some similarity is, so sort of along the line of thought that Eschelon was talking about. Okay, so you can sort of see some similarity in the physical world, like the mass and the energy, the time and the length scale, and then you see, oh, so I see some of the similar properties in the compute system. So sort of along that, I was thinking, Tad, you just sort of drew a picture, right? So the fundamental the geography, not the geography, the structure, right? So that you can zoom in and then look at a micro scale of the universe and say, hey, here's a mass boundary, and then you have like 8 divisions, right? So you could like in 8 ways to further divide things into pieces. And then for charge boundary, right? So there are like a certain division. So back to the compute system, I think for a modern compute system is built on top of the binary, right? So if you dig into the core, it's 0 and 1. It's like, okay, so it's a fundamental basis of 2, right? So for a modern computer, the fundamental basis is 2. And then Tad, you were thinking, so okay, for a physical universe, you have like a 5 different boundary, right? So there are like the length, time, charge, mass, and temperature, right? And then you double cover it, double fold it, and then you got 10. So that's sort of the natural the base of 10 where it comes from. And then for a computer, it's like, okay, so if I just follow that same logic, I see 0 and 1, right? So and then if you want to say, hey, so now I have this very fundamental the division, the 0 and 1, and then I go one level up and say, hey, so but sometimes I have I group things into a byte, right? So sort of that's kind of the natural things. I group things, right? So and then, hey, a byte. I mean, maybe just a choice, because when you design the computer system, you have the choice that you can design things, but it comes out that the byte is like it's just a third order of 2, right? So and then you can just multiply on top of that. So it seems a natural choice. Maybe you could choose 4, right? So, or maybe you could choose like maybe 16. But yeah, 8 seems like okay, an interesting choice. And then with the 8, and then you can say, hey, whatever the number, like let's say within 256, I can divide it like 8 ways. Then I get 0, 1, 1, 0, 0, 1, 1, right? So there is a specific sequence of digits that would represent this thing.
That division structure.
Yeah, the division. And then it has a very specific meaning. So in that context, so and then you think about the memory, right? So we're thinking about the memory has some of the characteristic of space. And say, yeah, what a memory is, I have a bunch of these bytes, right? So like located. Oh, okay. Yeah, so I have like a lot of number of these bytes, right? So maybe the bytes are organized into like a certain higher level data structure, right? So I could build an array of certain numbers or something. Yeah. Or maybe I'll just hold it. Yeah. Yeah. So there's a pin. Okay. And then you can continue to build like a more and more complex data structure. And then when you get to, then the thing is, okay, now what is compute, right? So if it is just a piece of data, like 128 stored in a byte in the memory somewhere, it doesn't change, it doesn't do anything. There's no dynamics, right? So there is, so as the clock tips, yeah. So now you have to introduce some dynamics. Because okay, the clock is ticking, right? So we say, hey, so I have like a 1 gigahertz, right? The clock is ticking, so that's the finest division. I mean, it is true, right? So if it is ticking like a 1 giga, 10 to the 9 times per second, so you can't go beyond that, right? So that's the fundamental division of time within a second, like
Of the thing
whatever.
that's thinking, the
Yeah,
computer.
yeah, that's the fundamental, the ticking, the clock. And then, so what I'm thinking, the computer is, if you have one CPU core, let's just say, and then it looks like there's one sort of place of the compute engine where you retrieve a piece of information, and then you do something, okay? Then maybe you have some instruction. It's like a source code, right? So you have some instruction. Okay, I take two pieces, I take two particles, and I do a addition, I do a subtraction, or some action, right? So, and then the action could be on one object, right? So I simply do a negation, right? So, or just do the negative for something, or I just take two, and then I give you the product of the two, right? Or I do some shift, right? So the digit. So, and then I get a new thing, and then I push into another place in the memory, right? So, and now the time becomes meaningful because I have a dynamics, right? So
Then the time is naturally meaningful in terms of the dynamics.
yeah, in terms of that dynamics, because okay, so that this particular computation takes like a one step. Okay, so I just do like the gate just negated, and okay, I get it. So or maybe something that takes naturally takes 3 ticks, right, to compute that something. Um, So, okay, that's an interesting sort of analogy. Okay, so, and then the other thing is, okay, what if you, then I have only one core to go through all these changes, right? So that's kind of a bottleneck, right? So it's not very fast. What if I have huge amount of data? I need to sort of increase the throughput. And so, okay, now you have multi-cores, right? Or GPUs, right? So you have like thousands of these cores, and then you can have these thousands of CPUs across different nodes, right? So crunching, you can divide the data. So, and now the way I'm thinking is you have a local clock, right? So you have, let's say you have a multi-thread. So I have two pieces information, and then they diverges. Okay, so originally at this time point they're together, right? So we're loaded together, or they're in sync, but then they got divergent. So this one that moves into this core, a thread. So let's say into this thread, and then this piece of data structure that goes into another thread. So now the time takes a relative sense. In a sense, this core might be running at like a 1.2 gigahertz. This one might be running at like
they have
local time, right?
Yeah.
Yeah, local time. So before they emerges, their time are irrelevant because I'm on my local time, you're on your local time. So before we actually meet and shake hands, resync again. So so actually, I don't know about exactly what is happening on the other thread. And then, so sort of like, okay, there is this little bit the relative sense that comes into the picture if you have these multi-threaded thing, the multi-processing. But in the universe, now we're thinking, so what is compute, right? So if you think, I mean, so people nowadays are talking about, okay, so think about, oh, we're living simulation or whatever, right? So that might be a stretch too far. But however, I don't think it is a stretch very far if you can consider at the fundamental level, you have some structure, and then there are some rules to apply these changes at a certain time steps, right? So according to certain these clock ticks, right? So that things are changing from this state to that state, given certain condition, right? So if you have a temperature like high enough, and then maybe okay, so maybe there was a barrier, you couldn't like morph from this element to this element, right? So so it's only chemistry, right? But you cannot like change from this element to this element. But once you go over a certain like a local condition, right? So something could happen, right? But locally it is doing that. And then at a different location, it is also happening. So, but from like a theory of relativity, at least a special relativity standpoint, right? So, but this computation happens locally here, and then another thing happen somewhere there. So before they exchange information to sync their state, they basically just go on their own clock, right? So they're right. So this is sort of okay. So if you think the universe as a compute engine, maybe they are distributed, right? So they have these compute cores or compute engines everywhere. They're doing this local changes, dynamics, right? So somewhere else, okay, they're doing that, and then everything is happening in parallel and all
You can
together.
take advantage of making things on purpose be computed where they have faster time.
Yeah. So maybe, okay, so the things are ticking a little bit faster, right? So maybe when you have a lot of mass, I mean, I don't know, maybe then things tend to being dragged down a little bit, right? So things happen like when you have a huge mass, okay, so naturally the clock ticks slower. Maybe eventually, okay, if you have a black hole, then the whole thing, the time loses meaning, right? So okay, so it's all mass. Okay, there's no time. And then everything sort of from that perspective sort of stay constant, but somewhere else the things are just moving, right? And then so I think from that view you could also have an intuition on why this like a locality, right? So this like a theory of relativity, right? So that might make sense, make intuitive sense, right? Yeah, just some thought like trying to connect like a computation, right? So in a computer, well, where I think it's probably a simplified version of a universe. I mean, so in some sense, it is probably a universe.
System, yeah.
Yes, it's a closed loop. It's a closed system, right? So it can perform all these things. It can simulate other more complex things. So maybe technically it is something, right? So whether you call it.
To just piggyback off what you were saying, one of the things that Professor Wolfram had discovered when he was writing his big book, A New Kind of Science, was for every, let's take for instance, element of computation, some may view that as perhaps a tick of a clock, perhaps time if you would,
Right.
the underlying patterns of cellular automata,
Just
they end up breaking up into 4 primary articulations.
Yeah.
And that apparently seems to hold for at least all one-dimensional and I think two-dimensional cellular automata.
The cellular automata.
But I just found it interesting that for every element of computation, there were 4 essentially primary actions that ended up evolving in different ways. That may be computationally irreducible, so sometimes you need to literally play the game out to see what happens.
Right.
That was kind of cool.
Yeah, it's kind of interesting, right? And then it goes back and say, hey, it feels like it's a computation. So when you have a computation, you need a chain, and then when you need a chain, you need something like to represent time. And then okay, so now we have time, and then you have all the other things. So maybe when things are shifting according to with respect to time, that's what we call dynamics, or maybe simply just computation, right? So if you're like changing according to certain rules, well, technically it is computation.
Yeah, it is.
Yeah. Well, yeah.
Oh, you're done.
You know, coming back to what you said about a black hole, the closest thing in programming that I see that is close to a black hole is a database. Because a database has mass, right? But the charge, nothing's interacting, so the charge dimension is squeezed out of it. The time dimension is squeezed out of it. But you can also argue that it has the space dimension, right? There's space in there, and there's mass in there. I'm not sure if there's temperature in there. So I don't know if it's valid, if it's making a leap, that if you look at a database and say, well, could we say the same thing about a black hole? Could we say a black hole has space and mass, but no time and no charge? And I'm not even sure about temperature. But are they really closely analogous? Sometimes I feel like I can go 2 ways. I can go backwards and forward. You know, from thinking from the programming point of view, can it give some insights? And one of the things that I found also about using the laws of physics in programming, it gives us a point to agree on. Like, one of the goodness in programming is that, you know, in concept we write code and we build things that are do a single purpose, right? You tend to write a good function should be very unique, it should be atomic, and do one thing and one thing only. The problem is we don't always agree on what that one thing is. Like if I have a program where I'm gonna, I don't know, give everybody a raise by 10%, and you write the program and you have like an employee record and maybe their salary is in there, and you can read a record from the database and give it to the employee calculator and then get the record back and save it. Or another argument is that the employee record reads itself and then, writes itself. And people could argue either way, say, well, the employee record is not atomic anymore because it's reading, it's writing, and calculating. And other people could say, well, that really is an atomic operation. It's composed of these things. But once we have the laws of physics, we now can agree on what the atomic things are in programming. Does this belong in the gravity field? Does this belong in charge?
And we have reasons that are clear for why. Instead of just confusion and someone went with it as a guess.
As a guess. And we can all look at programs and agree. And my intuition tells me that if it aligns, the universe has already figured out what's atomic. What are the base components? So right?
Yeah.
So if we look at the base components in programming and relate it to physics, we can now kind of agree on what belongs together and what doesn't.
That's a perfect segue for me to take 30 seconds at least. The equation that we're writing up on the board that I'm working with all the time, that's literally as I conceive of what they are. We have a base geometry that does so many unique things in it. It breaks into so many number of pieces, but all those pieces are doing different things. So if you collected all the unique things that it's doing, every one of those is a geometric transform, an equation. There's going to be some equality because everything's balanced, but the equality can turn into different numbers of things doing different things to each other. So every equation, as I see, would you agree with this, counts as a program available by the computer intrinsically. It's all of the programmed parts of the computer.
Yes.
Okay. So then the goal after that is recognize all of its intrinsic gears, all of its internal program parts, and then learn how to think using those as the steps of thought, right?
Right, and
Okay.
build up from there.
But hopefully this gets you to get even more curious, stare more at these programs we're claiming. If you understood the prescriptions of these equations as programs, if you start to see what transform is each one talking about, and look at the symmetries between the transforms each unique one talks about, I think that'll start guiding the programming intuition. That's my hope. I think it's the smartest way to be guided by the logic you can get from the nature itself, and try to use that as the logic as your framing logic.
Actually, I think that would be success in the physics programming library because it has to be made up of the math.
Mm-hmm.
If it's not, then we're cheating.
Yeah,
And
then there's a part that we don't know what we're doing. Yeah.
We don't know what we're doing, and I found over the years of building this library, whenever I cheat, it's always wrong.
Yeah.
It just...
You can hack it. Does the universe agree that that's an acceptable hack to continue on?
Right,
Yeah,
and can I use it all the time? The thing, even when I was talking about diodes and capacitor relationships, in the real world of physics, we can change what the diode is made out of. We can change the materials, but a diode is still a concept that exists, forever. Once it's all concepts, and
it's a relationship.
It's a relationship. Now, there's been a lot of design pattern books published in programming, but I tend to. There's a really famous book, they call it The Gang of Four. It's a white book with all kinds of programming design patterns, and and you'll see good design patterns for React programming and design patterns for this, but they're always, they're not based on anything that's real. What I found is that nature has all the design patterns. If we're inventing a pattern, we're probably doing it wrong. And if we just pull from what already exists in nature and see how it's computed, coming back to the diode, in in electronics, we can change the materials that the diode is made out of, but the diode is kind of an inherent design pattern, right? And if we had done programming that way from the beginning, we would have the standard set of patterns that would map to the laws of physics. We can change languages. We're not doing COBOL or assembler anymore. We're migrating to higher languages, but all that we learned in the patterns over the years would still be true.
So by extracting underlying code, which is real, will better help us construct things that to our mind are imaginary, but based off of reality to the best of our knowledge.
And
Right.
produce the things we currently call real. Yeah.
Yeah, and then, an example of where, and this is where I borrowed from neurons from our nervous system to solve one of the hardest things to do in programming is event handling. And there's a lot of arguments in that because, you can have a button on the screen and you press the print button and you can write hard-coded code that runs some code to do a print, and the problem with that is I can't reuse this code because it's tied to this print button, and I want to really run this code separate and throw it at some kind of event and let it run on its own and break it up. And it's called decoupling. This is very tightly coupled. And the argument is that if you couple code very tightly, then you can't reuse it very easily. So that's wrong. So then you go the other extreme. You have event handling. And the print, when you press this button, all this button does is throws an event. Print was detected. And then this little routine is running and it's listening for events and it's getting all the events. It's like save to disk, not mine. Read from disk, not mine. Print, oh, that's for me. So I'll print it. And it's completely independent. And then the people who say decoupled code is reusable, they all cheer. We've now found a way to handle this. Except there's problems with that because what if you want to print and save? You want to save the record first and then print what you saved. Well, now you have another routine, a save routine that's running. And it's also listening for events. It's listening when it gets that print event, maybe it'll do the save. And then when it gets the print event, it'll actually do the print. But, or it'll read the record that it saved. But there's no way to guarantee the order these things will fire. So if this gets the event first, it'll print it and then it'll save it and it'll be wrong. And another problem with highly decoupled code, it's very hard to debug it because you press that button and it throws an event. And it's like, who's listening for this event? What program is registered? Now you're grepping the code and trying to find it. It becomes incredibly difficult. So now we've achieved complete decoupling, which makes our code reusable, but now it's impossible to debug. And we can't find... and when these things come out of order, because I've run into things where you have multiple things listening in the same event, you can't really control the order that it's done. So I was looking for a pattern in nature. You can read all kinds of articles and everyone has an opinion on how to do event handling. But is there an example in nature where you have a lot of decoupling, but also a way to control the order of events? And if you look at the typical neuron, it has, it fires synapses and you can wire them together. So let's say you have the print program or a print button and it has its neuron in it. And I want to save, so I can wire this neuron. So when the synapse fires, this one is tied to the save. And then I put another neuron in order, it fires this, or I can daisy chain it off of that. This one fires and then it does the print. And I found you accomplish both things. You decouple the code. This is completely standalone. It fires when it gets an event from a neuron. And this one fires when it gets an event from a neuron, but it has kind of a nervous system. So it's very easy to debug because now you do print, you see where this neuron fires, where does this for? It goes to here, then this goes. So now I can have a complete map. And it's like, where did I get that from? Well, nature, our nervous system. So I started wiring my programs together with neurons. and doing all my event handling with neurons, and I got the encapsulation fell out of it naturally. This is a self-contained program that runs when it's told to run, not by listening to random events and trying to decouple, but now I have the wiring, but it is coupled. It's coupled enough to be debugged because you have a nervous system, and things only happen in the way that they happen in the right order. And that's an example of pulling from nature. I didn't try to invent anything. It was more trying to look at how things really work. This concept, if we invented it in 1990, in 2023, that concept would still exist. We might write it in different languages, do it in different ways. We may even have compilers that can generate some of this code for us, but it's very predictable, and it's a behavior that we can all talk about and agree on how it works. So I'm finding that not only is programming in this way looking not only from patterns in physics, but I also look for patterns in nature when I'm trying to write my programs. Rather than reading a design pattern book, I'm looking for patterns in nature to use and just reuse them. And it seems like for all kinds of programming, there's a pattern for it already. I think that part of the whole concept of programming with physics is also adopting a mentality that we no longer try to invent our own patterns, right? We use what is already there and derive everything. Even these neurons, I didn't make the connections all the way down. Like it's easier to go from physics to chemistry and physics to electronics than go from physics to biology. That's kind of a big leap. It's like I would use atoms and things inside the neurons, but I'm not replicating all the behaviors of how neurons actually work, because that's like somebody can probably spend their entire life programming this to simulate, like using chemistry and physics to actually create a working neuron is a major project. So in some cases there are some hacks in there, but the concepts, I'm still using the patterns. And each part of this library, for anyone who's interested in doing, somebody could work on this, and we can build out an amazing programming library. One thing that I found is that by doing this, one of the reasons I can make messages very small and transmit messages from machines to machines and reproduce what's on the other side is by using the physics library. There's now an advantage we don't have before. I can send a message to another machine knowing what's running on the other side. I don't have to care if they wrote it in Python, if they wrote it in Java, or if they, whatever language they choose, they're running a physics library. So they have all the same concepts on the other side. So now my message doesn't have to transmit as much information as we normally do. And like when you transmit JSON, for example, you lose information. The class information isn't in there. You could start out with classes that you serialize. You have an object of type address, but it comes across on the other side as name, address, city, state, zip, but it doesn't have the class information called address. So you tend to have to write a lot of code to reproduce it. But if you already know that everybody everywhere is using the same library, messages everywhere become smaller, simpler, easier to understand, and easy to work with. So, that's the first phase. Like, I'm kind of tired of talking, but that's the idea.
One step closer.
No, I like that, because rather than attempting to use full brute force genius level intellect to try to just come up with some conceptualization, we're going along more the lines of discovering what's already there. And if this is an underlying part of the code of nature, that just inherently should help us build programs that we use as human beings.
Which is why every time I try to invent my own programming library, by version 3 it turns to garbage. Because I'm just not as smart as the universe. I'm never going to be. Like, these patterns are all over the place. We're going about it wrong. And that's why, because software engineering is not engineering, That's why we're on, what do you call those, when you treadmills, like
Yeah,
we're literally on a software treadmill. We're not making progress. We're scrapping what they did before and doing it again. This is and it's like we're doing it over and over again. So, this will allow us to finally make progress. And
I had always wondered, because as a dude that spent far too much time on the internet, I'm like, okay, once we start getting broadband, I'm like, oh, that's cool, it's fast. And I've noticed it's like, yeah, we're increasing like the video resolution, this and that, but it's like a lot just standard web pages. The web doesn't really seem that much faster than
No.
it has been. And I'm like, why is this? Is it because we're on like the infinite tower of turtles and everything, but we don't actually know what a turtle is?
that's like, you've heard me complain about that too. Exactly that. It's like, I'd press a button and it's like, you got to be kidding. This machine is 1,000,000 times faster than it was 10 years ago, with 1,000,000 times the memory and 1,000,000 times faster network speed. And why is this slow? But what's happening is because we're inventing so much stuff that to write the average program, you'll have 1,000 packages that you downloaded of open source, and they all work different. And they're,
It's adequate, but if Echelon, if what you're talking about is true, I mean, it could just be so much better.
Oh, and it is like,
And
I
universal and permanent. So it's like learning a language. It's not learning a code for language. It's learning the code for language. Because everything you learn from then on out is universally applicable. For sure.
And I found that my physics programs, when I write servers and things, they're tiny. They're so small. And it's because in conventional programming, you're reprogramming the same concepts in 10 different ways. You download some open source that they wrote the same thing you wrote with the same with slightly different You just have copies and copies and copies, because there's no universal way of doing it. With this, there is. So I find that my code gets completely refactored down to tiny, tiny little things. And it's like, I've done this before here. This is one of those. Because also it's easy to factor your code in a way in terms of what are the atomic things. And it's like, oh, well, this seems like it uses gravity. So let me go to that piece of the code and like reuse this here. This is using atoms. This is using molecules. The concepts are all there. And as the library builds, in theory, take many years and many people working on it, we'll have the complete model of chemistry and electronics. And, what a wonderful way to program. You know what I mean? There's actually right ways to do it. And we all have a common language that we can talk about. And, that's so lacking in programming. It's, you download some new product and Google it, and it has its own terminology, and, and it works completely different.
With a finite level number of categories, you have the ability to actually do iterations continually to get what you have, and whatever graphic user interface you happen to choose to use, if the underlying code is essentially talking about the same things. I mean, who cares what it looks like when you're programming? Use whatever realm you want, but you can get the right answers, and it's more effective, and it helps move us forward. Sounds like a win.
Yeah. And if you think about messaging systems, how easy would it be to send a message to another computer if you know the concepts that they're dealing with and that they understand? Like right now, it's like we send things and then we have to document it, and the whole process starts over. I don't have to care what language it is. I just know you understand this message. So
Cool.
that's it.
One thing, just, it's not a question, but I know nothing about programming and nothing about neural networks in the brain. But I've been reading lately about the comparison between, let's say, the neural network in the brain of a human and that of an octopus. We have a very powerful locus, right, of our brain here, and not in our nodes, not very much. Whereas the octopus has a very small brain and big nodes around.
Which don't act like brains, right?
Yeah, so depending on the system, if he wants to get in a bottle, this node can take over.
Oh, wow.
And send information back to the big brain. And it's very much like I hear that the military is organizing its, say, command structure for platoons in the field. Supposing there's one commander and five squads out, right? Now the original structure is for the command to receive information all of the squads. And if one squad engages the enemy He calls back to the commander directs the other guys, he calls the bombers to come in and hit those guys. But with this type of program, that squad takes command and then can give information back and have a much more effective response.
The one who's most desperately in the situation.
Yeah, he can call in the bombers. He can tell the other squads what to do.
Huh.
So I'm just wondering if this is sort of what you're talking about, or if this is coming in right now.
Well, that's also similar to, I think, was in the Top Gun movie. Some folks that were talking about some of the modern technology used in some like the F-16s and stuff like that. And basically, they actually have their own separate computers and components to just keep relaying whatever the mission information it is between the different units, the different parameters in the aircraft, to be able to realize it to the pilots as well, and everything. So, I mean, that is something that's we use as technology as well, yeah.
But it seems like it might help in programs.
Yeah, and I also believe that unless we start programming in physics, we're never going to solve this problem of the mathematics. Like, we have to, we're not going to do it by downloading some open source product and see how we can do it with this. We got to go all the way down. And this is the only way I think that we'll be able to do it. You know, it's the right way.
It's true universal computing.
It's true universal computing, and it's based on all the same ideas. You know, then the title software engineer will finally mean something. Because right now it's like, you know, on my resume I have software engineer because that's what everyone wants to hear, but I cringe. Like, if anyone asks me, I'm a programmer. I'm not a software engineer. Until this is done, I will never be a software engineer, and neither will anyone else.